I think we're all ready, so we can start. Vamos a empezar la segunda conferencia de esta serie. Ya son unas cuantas series las que hemos tenido aquí, gracias a la profesora Achúcarro. Esta noche tenemos con nosotros una de las personalidades, sin duda, más destacadas de la cosmología en estos momentos. El profesor James Peebles es el Albert Einstein Emeritus Professor of Science de la Universidad de Princeton, Estados Unidos. Nació en Canadá, hizo su doctorado en Princeton en el año 1962 con nada menos que el gran Robert Dicke. Y se quedó en Princeton desde entonces. Parece ser que le gustó aquello. El profesor Peebles es uno de los más famosos cosmólogos, como decía. En particular, es uno de los autores, junto con Dicke, Roll y Wilkinson, del artículo que acompaña el descubrimiento del fondo cósmico de microondas por Penzias y Wilson, hace 50 años. De hecho, este año celebramos el 50 aniversario, explicando al resto del mundo, aquellos que no se habían enterado, en qué consistía ese criptográfico título de medición del exceso de temperatura en la antena de 4 gigahercios del artículo de Penzias y Wilson. El profesor Peebles ha hecho contribuciones esenciales para la comprensión no solamente del fondo de radiación y de la expansión del universo, también de la expansión acelerada del universo y la estructura a muy gran escala del universo. Es el primer autor de varios centenares de artículos y al menos 2 libros muy influyentes. Esencialmente, libros que todos los alumnos, estudiantes de universidad que estudian cosmología y gravitación han tenido en sus manos. Y no solamente los estudiantes, también los investigadores. Y eso los han estudiado, no solamente lo han usado durante la carrera, lo han seguido usando a lo largo de sus experiencias investigadoras. El profesor Peebles, además, ha sido galardonado con múltiples medallas. En realidad, el número de medallas es impresionante. Yo, si me lo permiten, me voy a concentrar solamente en 2, la primera y la última. La primera es del año 1981, la medalla Eddington, y la última en el año 2013, la medalla Dirac, enormemente prestigiosa, y cito, se lo dieron por su trabajo independiente y pionero a lo largo de toda su carrera, esclareciendo muchos aspectos de la física fundamental, la cosmología y la astrofísica. Entre sus muchos premios y distinciones se encuentran el prestigioso premio Shaw, el premio Gruber, el premio Crawford de la Academia Sueca de Ciencias, y es además miembro de la Royal Society de Londres. Estamos hablando de una personalidad sin duda alguna. Así como de las 2 academias más relevantes, la National Academy of Science americana y the American Academy of Arts and Sciences. Pero quizá lo más importante es que el profesor Peebles es el padre de la cosmología moderna, al menos tal como la entendemos hoy en día. Sigue siendo un cosmólogo extraordinariamente creativo y muy activo, lo hablábamos hace un momento en la sala, con un amplísimo conocimiento de muchas áreas de la física y la astrofísica, y estoy seguro de que eso quedará manifiesto durante su charla. Así que, sin más dilación, le paso la palabra al profesor Peebles. Gracias.
Juan, thank you for those remarks. They were very kind. Ladies and gentlemen, it is a real pleasure to see you here. And I hope you will have some pleasure in hearing what is known about the nature of the universe on large scales, and I think equally important, how people came upon this knowledge. So let us first notice this image of the sky at night, showing a band of light from the stars in our galaxy. Our galaxy is shaped like a disk or perhaps a pancake with rough edges. You see dark bands through the starlight. That is where interstellar dust has collected and is absorbing the starlight. There are many galaxies like our own. Here is a nearby example. This disk of gas and stars and dust happens to be seen nearly face-on. The center is rotating more rapidly than the outside. That causes the elegant spiral structure. You see dark lanes where, again, dust has settled and is absorbing starlight. You see perhaps blue regions and some red regions where interstellar gas has settled and become dense enough to collapse to new generations of stars. In a new generation of stars, the most massive are by far the most luminous. Their surfaces are hot, making blue light. That same hot surface emits ionizing radiation that produces plasma in places. Can you see here, perhaps in here, where the interstellar matter, mostly hydrogen, has been ionized and is recombining and making a red line characteristic of hydrogen. You see perhaps in the center a bluish or a yellowish glow, which in fact extends through the whole of the galaxy, light from stars with mass similar to that of our sun. We know that in our galaxy, there are at least as many planets around stars as there are stars. There are some 10,000 million stars, roughly similar to the sun in this galaxy. It's a good bet that there are some 10,000 million planets in this galaxy on which all manner of wonderful things are happening that we, the human race, will never see. Here are examples of other nearby large galaxies in the bottom of the figure. This one is almost flat. You see it nearly edge on, and you see a rough surface, but nothing sticking out very much. Here, you see again a flat disk, but a bulge of older stars toward the center. Here, somehow it's cut off, a galaxy that is all bulge, no disk in particular. Above, you see images of a few less luminous galaxies. There are many more of them. Above that, you see a map in orthogonal projections of the known galaxies within a distance of 25 million light years. The red dots mark the 20 most luminous galaxies. They're all roughly of this character. The less luminous galaxies are typically a little less regular. There are irregular large galaxies too, but they're not common. You notice that the distribution of some 270 galaxies in this region is very irregular. Dense concentrations here and here. In this region, only one galaxy is well known. It's this one. This is plotted as a negative. Where it's dark, there are stars. A pathetic little thing occupying perhaps a third of the volume. The point here, the distribution of galaxies is exceedingly clumpy. Here is a particularly big, rich clump of galaxies. Each of these dots represents a large galaxy. The distribution of galaxies is a very characteristic form, a tight concentration and then trailing off in an irregular way. It is similar to the distribution of stars in a disk-free galaxy. This is a galaxy of galaxies. Here is this same rich concentration of galaxies in the foreground of this map showing the distribution across this much of the sky of the nearest, brightest million galaxies. This is the texture of our universe. It's an historic image, and it's well an occasion to pause and look at the people who make these images possible and make the images themselves. Here is Donald Shane, director of the observatory at the Lick Observatory in Southern California. He spent 10 years of his life mapping out the nearest, brightest 1 million galaxies. He did this by hand with a traveling microscope on photographic plates, in pencil recording the data. Before the era of high-speed computers, what do you do with a million pieces of data? Very little, yet he and his colleague Carl Wertman took the data with such care that when high-speed computers came along, we, and a large part was the expertise of these then young graduate students, Jim Fry, Ray Sanera, Michael Seldner, were able to take Donald's data and turn it into an image. And I had the deep pleasure of taking that image to Donald and asking him, "So is this what you saw?" He laughed and said, "I was looking at this one galaxy at a time." I propose now to show you an image of the universe on still larger scale. To do that, I should introduce a new phenomenon. Here is an image of the center of our galaxy. It is very complicated because of all of the gas clouds, the dust clouds. But there is in the center a very compact, massive object. So massive, around 2 million times the mass of the sun, and so compact that as best we understand, it is a black hole, a relativistic collapse into which everything falls, including light. Nothing escapes aside from thermal radiation at its surface. We know this very well because one can follow stars quite near the black hole and follow their orbits, shown here. These data points are the positions of the stars, different each year as the stars move around this concentration. Knowing the orbits of the stars, you know very well that mass in the center. We should, on occasion, again, take notice of the people who made these things possible. These were the two leaders in developing this technology: Andrea Ghez, USA, Reinhard Genzel, Germany, on the occasion of a distinguished award for this wonderful achievement. So now you also notice in this, this central massive compact object on occasion emits bursts of X-rays. It also emits a more steady glow of radio. Other galaxies have more activity associated with their central black hole. Here is one of the ellipticals that is all bulge. Looking closely at the center, you see a dot of light, and from it a jet of light, relativistic particles that are emitted from that black hole. It's thought that it must be because material is falling onto the black hole, tumbling in, getting very heated, and shooting out jets of radiation. In some cases, these explosive jets can be very prominent. Here, the galaxy is buried in the center here. You see a jet of relativistic particles that fill these lobes with plasma and magnetic field. The plasma in the magnetic field emits radio radiation. This is an image at 6 centimeters wavelength obtained in the array of radio telescopes in New Mexico in the USA. These objects of this character are so luminous in radio that they can be seen at enormous distances. And here, a map of the nearest 10,000 such sources is probing out nearly to the edge of our visible universe. We must be careful with this image. It can be confusing. First, nothing plotted in the center because the telescope could not reach that part of the sky. Second, I will describe an event soon that will explain why there's no data here. You must be cautious about that point. That is that very luminous radio galaxy I just showed you. It is so bright that it confuses the instrument in the neighborhood. The absence of detected sources here is simply a technical problem with detecting a faint radio source behind this very luminous nearby one. Here another. And then finally along here you see a band of sources that are not at great distance. These are exploding stars in our galaxy. Apart from that, what do you see? Nothing. Again, a historic image. So we should look at the radio telescope on which these data were obtained in West Virginia. This was built many years ago and built with rather little regard for engineering safety. It was inevitable then that it would collapse, and it did, as the survey was winding down. It's all right. There were no injuries, and there was at the time the senior senator from West Virginia, Robert Byrd, had great influence and was not about to let the great state of West Virginia lose a major scientific instrument. He somehow found funds to build a new, bigger, better telescope. But let's return again to notice this. In natural science, we operate on different scales. There are those who study atoms, those who study the properties of atoms at the nuclear physics level, those who study the elementary particles within the nuclear physics all the way down to the Higgs. Or you may study how atoms arrange themselves in molecules, or the molecules in solids. We may study the way the molecules are arranged on the surface of the Earth, of the other planets. We may study the way the planets are distributed around stars, the way stars are distributed in galaxies, the way galaxies are distributed in groups and clusters. And we see that, in fact, the clusters of the sort I showed you are arranged in superclusters. But beyond that, something new, nothing. That is a remarkable concept, transformative. The universe, on this scale, has no structure. That is important because it tells us we can make a theory of the universe. If the universe had endless layers of structure on ever larger scales, we could make theories of parts, this or that structure, but we could not make a theory of the universe. That theory is possible because the universe is seen to be very close to uniform. And we can follow that near uniform evolution. So we have the notion of an expanding universe to discuss next. I will return to this image and an explanation of the text and that curious figure later. For the moment, let us just consider this as an analog for our expanding universe. Imagine that we live in 2 dimensions, not 3. Imagine we live on the surface of that balloon. You must not ask me, what about the space above and below the balloon? No, we live on the balloon. That's all you have. Okay? Imagine that the balloon is being blown up. That's easy to imagine. We must be careful again. You and I are not expanding, and our galaxy is not expanding. But the distances between the galaxies are increasing. And you see a neat pattern. You live on a galaxy, perhaps here. You look at the neighboring galaxies, and you see, as the balloon expands, they're moving away from you. You are entitled to say, the universe is expanding, and it's expanding away from me. But if you go to another galaxy, you will see the same story. An elegant arrangement. Everybody thinks that the universe is expanding away from them. But there is no center of expansion. And you must remember, of course, you can't think about the center of the balloon. You live on the surface. 2 dimensions. And in fact, this is the pattern of motion of the galaxies away from us. 1929, Hubble discovered distance is increasing in this direction, and velocity of motion of the galaxies away from us, and remember it's the same story for anyone else in another galaxy, are moving away from us, and they're moving away faster in direct proportion to the distance. This is the discovery, 1929. Here, 1936, a continuation. Already in 1936, when I was 1 year old, astronomers were measuring galaxies moving away from us at 1/10 the velocity of light. A remarkable advance. I propose to just take a minute to look at some of the figures of people responsible for these early developments. Albert Einstein, 100 years ago this year, invented his theory of general relativity. 2 years later, he argued that a sensible universe would be uniform on the large scale. Just that image that you saw in the map of radio galaxies. His argument was purely philosophical. He was right. The big open question, was he right for the right reason? We have no answer. But we can continue to notice that Alexander Friedman, Russian, saw that in Einstein's idea of a uniform universe, the universe could, in general relativity theory, expand or contract. Unfortunately, he died young and before there was any evidence that the universe might be doing this expansion. Percival Lowell should be mentioned. He was a member of a prominent Boston family, socially very influential and very rich. he developed an interest in the idea that Mars may have an advanced civilization that's building canals. It was a time when there was big canal building on Earth. It's natural to imagine that if there's another civilization in another planet, they'll build canals. He used his own fortune to build an observatory. His memory is honored by astronomers because he built the observatory in a good site for observation in Arizona, and because he hired first-rate astronomers to instrument and use the observatory. In particular, Melvin Slipher. This has all been, Melvin Slipher is here, built the instrument that was capable of measuring the spectrum of a galaxy, the energy distribution as a function of wavelength. He made the capital discovery that the galaxies seem to be moving away from us, as inferred by the Doppler shift. You've all experienced the Doppler shift. You stand by the side of the road. You hear the cars going by. Boom. As the cars are approaching, the noise in the engine is compressed to shorter wavelength. As the cars move away, the noise is stretched to longer wavelengths, lower tone. The same with light, and in particular, the light from galaxies is shifted toward the red as if they're moving away from us, and the shift directly proportional to distance. That key point, the shift directly proportional to distance, was discovered through the courtesy of Henrietta Leavitt, who showed how you can use variable stars to measure distances to galaxies, and to Edwin Hubble in California, who used the Leavitt relation to infer distances to galaxies. So at the end of toward the end of the 1920s, people had apparent recession of the galaxies moving away from us. People had distances to galaxies. It was the Belgian, Georges Lemaitre, here, who put the two together and gave us the first solid theory for the expansion of the universe. And then it was, Lemaitre published his idea in 1927, and being Belgian, I suppose, he published his results in a Belgian journal that I'm sure was a very fine operation, but it was not read by the old boy network, if I may say. He is fortunate that he had spent time studying with Eddington in England at Cambridge University. After several attempts, he managed to get Eddington to pay attention to his ideas. When Eddington did pay attention, he soon realized that Lemaitre may be onto something important. He told his colleague, Willem de Sitter, director of the Leiden Observatory in the Netherlands. By the way, here is a certification. I certify that Abbé Georges Lemaitre has been attending my lectures to my entire satisfaction during the academic year, 23-24. Arthur Stanley Eddington, very good. So, he made contact. We have evidence of the contact. Here is a letter from Eddington, dated Cambridge, 1930, to Professor Willem de Sitter, Sterrenwacht, well, the observatory, Leiden, Holland. The text, kind of fun to read. Eddington gives de Sitter Lemaitre's address. A student and I had been working on the problem, made considerable progress. It was a blow to us to find it done much more completely by Lemaitre. A blow softened, as far as I'm concerned, by the fact that Lemaitre was a student of mine. You learn that if you do something great, you'll make friends. De Sitter was so impressed by Lemaitre's idea that he wrote an article about it in a prominent Dutch newspaper. We will not attempt to read this, but to notice that it stimulated one of his colleagues to draw this cartoon of Professor Dr. Willem de Sitter, Professor Dr. Director Willem de Sitter. That's a reasonable likeliness of his face. We will not talk about the rest yet. But this was the article and the cartoon that made Lemaitre famous. In my opinion, he was the one most responsible for the idea of an expanding, evolving universe. Of course, to believe that, to put forward evidence that the universe is expanding, we need data of some, we need evidence. What one would hope to find is fossil remnants from that time when the universe was very different from now, much denser. This idea originated with George Gamow, shown here in a cartoon, about 1948. Gamow was one of the early refuseniks. He escaped from the Soviet Union in the late 1930s. He had the idea in the late 1940s that an elegant universe might be one that, when it was young, was dense and hot. The cartoon from that era, commenting on the thesis of Ralph Alpher, Gamow's student. Here is Robert Herman, an associate in the work. Here, a commentary. Scientist says world was created in 5 minutes. Well, maybe. You remember, if you're of a certain age, when we lived under the threat that there may be a nuclear exchange. I'm still somewhat amazed that we survived that. But this was a cartoon symbol of the hydrogen bomb, the super bomb. The notion was there, but and here is to illustrate the consequence. You're all familiar with the heat from a bonfire. You hold your hands out, they're warmed. That's thermal radiation. It had been worked out by this time and very carefully checked that if you let radiation relax to statistical equilibrium in a cavity, then the intensity of the radiation at each wavelength is determined by one thing, the temperature. You tell me the temperature, I'll tell you the intensity at each wavelength. So, who will measure the intensity of the radiation from the Big Bang? This can originate, I think, with my teacher, Bob Dickey, with Annie and their firstborn, Nancy, in about 1945. Bob Dickey was a student, a graduate student in physics in Rochester. As the war broke out in the U.S., the U.S. effort in the war, he rushed to MIT in Cambridge, Massachusetts, on the East Coast of the United States, to work on war research, principally the development of radar, which is an enormously powerful war tool, and now, of course, an enormously powerful peacetime tool. Here is a professor of physics at MIT pointing to a building that was erected in a hurry in early days of the U.S. involvement in the war. It is made of wood. It is a great historic relic. To my great distress, it was torn down just a few years ago. You can see why it's a fire hazard. You can see also why I deeply regret it. It's an historic fire hazard. On the roof of that building are these people during the war. Bob Dickey on the right, some of his associates, and an invention of Bob Dickey's, a device that is capable of detecting thermal radiation at microwave wavelengths in the order of a centimeter. Here, below, a sketch of the skyline seen from that building. At the time, there was still industry in Cambridge. The industries had smokestacks, and some of the smokestacks were warm. Above, you see a chart recording showing the response of Dickey's radiometer as it scanned the horizon and the beam passed over the chimneys. You see the deflection downward, which is to say in the direction of increasing temperature. This thing is just what is needed to detect the thermal radiation left over from a hot Big Bang. 20 years later, almost, Bob Dickey had the idea, independently of George Gamow, that the universe might have started out hot and that there may be a remnant, a fossil from that hot early universe, cooled thermal radiation. Why did we get that? He instructed 2 young members of his group, David Wilkinson on the right, holding the screwdriver in the plaid shirt, Peter Roll on the left, a Dickey radiometer designed specifically to look for this radiation. He, meanwhile, told me, why don't you go think about the theoretical implications? Those casual remarks set my entire career. I suppose signifying that one should be careful with casual remarks. But by that time, there had already been an interesting development. Here, 1959, a Bell Telephone Laboratory experiment in communication by microwave, that is to say, centimeter wave radiation. You see that this is a very rough early experiment. The wood holding the antenna is not planed, it's rough wood, a rough shack. But inside, some very very technical instrumentation, traveling wave maser amplifier, and here an indication of the engineer's search to find all sources of radiation. You don't want to have a lot of radiation around, it disturbs the detection of a signal. So they had done a careful accounting of sources of radiation received by the detector all along the channel. And you notice in particular what is circled, they had to assign, well, in convenient measures of temperature in degrees Kelvin, 2 degrees to radiation that originated in the ground, propagated up, curled around the horn antenna, and got its way into the instrument. That was a remarkable thing to do. They wanted to balance the books, but they knew perfectly well that this antenna is carefully designed to reject radiation from the back. Perhaps some of you remember when long-distance communication was by microwaves with these horn reflector antennas turned upright so that the antenna receives radiation from near the horizon. The reflector part bends the radiation down into the horn, down into a region where the radiation is amplified, then radiated out in horns pointing further on, a relay station. These horn antennas are designed with exquisite care to eliminate any radiation coming in from the backside. You can imagine how important that is if you pause to consider that if the radiating antenna shot a little radiation in the backward direction, and it was received from the backward direction by these receiving antennas, then you would amplify everything you were sending back, and you would get an echo that gives you the howl you can sometimes hear in an auditorium, but not here. Perhaps you've all experienced that howl. That is to be avoided, and it was avoided by the careful design of these horn reflector antennas. The problem at Bell Labs persisted for 5 years until these two young people, Bob Wilson on the left, Arnold Penzias on the right, using another of these horn reflector receiver experiments, tracked down every possible source of radiation they could think of. They deserve enormous credit for sticking to this job of searching out what was producing this radiation. They were at wit's end, and they did the next important thing for a scientist. Since they were confused, they complained. The complaints eventually reached Princeton University, where these people were building a radiometer to look for this radiation. And so the connection was made. Here is an image I showed at my first lecture at a scientific society. March 1965. You see in the horizontal axis wavelength increasing to the left. You see above intensity of the radiation increasing upward. You see to the left radio background. There are those radio exploding galaxies that we discussed earlier. They are contributing radio to noise that we receive. But you notice that the radiation received by the Bell Labs experiment is well above what you would expect from those exploding galaxies. Stars are also producing some radiation at this wavelength, but a lot less. It was clear from the start that Penzias and Wilson and the Bell Labs telescope had detected something new. What is it? Well, my proposal in that talk was that it is thermal radiation from the Big Bang. If that's the case, then the measurement of intensity at one wavelength tells you a temperature, and the temperature tells you the intensity at every other wavelength. The audience at that talk were polite, but it was very clear they thought I was drawing an awfully large conclusion from a very limited piece of information. There was the second experiment, the Princeton one, soon completed. And by the end of by the following year, we had 2 points on this curve. Very encouraging. By the time I wrote my first book on cosmology a few years later, in 1970, we had lots of points on the left-hand part of this curve. But we had very little evidence about what happens when the curve is supposed to turn over and drop down. In fact, we had indications, as you see in that little triangle, that there was a lot more radiation than you would expect if this were thermal radiation from the Big Bang. That situation lasted another 20 years, finally to be resolved by 2 groups. This, a proposal submitted to the US Space Agency, NASA. You see David Wilkinson's name somewhere. You see John Mather. He was a young postdoc, and he took on the onerous job of project scientist. It was a brave thing for him to do, because this was going to be a space flight. 15 years later, he would sit and watch while his carefully designed instrument is placed on a rocket. And you know, sometimes those rockets explode. And he's lost 15 years of his career with no publications, no results. I don't think I could have stood it, but he is of sterner stuff. Here is a photograph. John Mather is in the background, the tallest person there. Dave Wilkinson is on the right. A crew of experts on the science end, backed up by expert engineers to build this great experiment. There was a second group led by Herb Gush at the University of British Columbia in Western Canada. He was trying the same technology to measure the radiation, but using a rocket rather than a satellite. The rocket, this first attempt, Black Brant 3B rocket. I have no idea what that is, but it was early primitive days. You notice 1973. Some 15 years later, let's pause and notice a picture, a photograph of Herb Gush, looking very scientific in that white coat. He's the only pure scientist I've ever seen wearing a white coat. Here are his 2 assistants, his 2 colleagues. Mark Halpern on the left, Ed Wishnow on the right. That was the team. And I must now confess to you that whenever I look at this photograph, I have to smile and ask myself, if I didn't know that these 3 people had done something great, and if all I had to judge these 2 by was this image, would it inspire confidence? Which is an illustration, I think, that I should not make such judgments. Here was the result obtained within months, after 15 years of labor, by the 2 groups. They are plotted in slightly different manners, so the curves don't look the same, but telling the same thing, that this radiation has a spectrum that is spectacularly close to thermal. John Mather received the Nobel Prize for the results of the top spectrum. I think it annoys me more than the principles involved in the bottom measurement, Gush, Halpern, Wishnow, that young people these days who are leading research in cosmology do not know about this bottom measurement. It falls to elderly people like me to keep them in line. You do have a history, you young men and women. Here is the modern situation. Again, the method of plotting is a little different, but the theme is the same. Unfortunately, you can't make out the theoretical curve, a very tiny line. The purple curve to the right is not a theory, that's a measurement of spectacular precision. To excellent accuracy, this radiation is thermal. The universe as it is now does not absorb or emit radiation very much at these wavelengths. There is no way the radiation in the universe as it is now could have relaxed to this thermal spectrum. This is evidence that the universe at one time was much denser and hotter and able to force the radiation to relax to equilibrium. Evidence that I would say is as compelling as the evidence from dinosaur footprints and bones and eggs that those improbable creatures walked the face of the earth. Compelling evidence that our universe has expanded, has evolved from a different state. Now, I show this slide, you're not supposed to look at this. You're instead supposed to be instructed that we have a theory of the expanding universe, general relativity. This theory will describe how the rate of expansion of the universe changes. How does the universe evolve? That depends on several quantities. The mass density in matter, the mass density in radiation, which has energy density, so it has mass density. There is a term that depends on the curvature of space sections. And there's a term called, in some cases, the cosmological constant, lambda, and these days, very fashionable, dark energy. This last term is allowed by Einstein's theory of gravitation. Einstein put the term in because it has the effect of pushing things apart. Gravity tends to draw things together. He took it as obvious and not worth discussing that the universe is forever, static. Since gravity tends to cause the universe to collapse, he needed a countering force. That was his lambda. He did not realize, or pause to consider, that his balance was unstable equilibrium, unstable. In Georges Lemaitre's first model for the expanding universe, he took Einstein's lead and imagined that the universe was at one time in this equilibrium, gravity pulling, lambda pushing, so they just balance. But he recognized that that's an unstable equilibrium, and that a slight disturbance could cause the universe either to contract or expand, and the evidence from the astronomers was it is expanding. This quote explains the situation in 1930, 9th July. Who, however, blows up the ball? What makes the universe expand or swell up? That is done by the lambda, the pushing. Another answer cannot be given. This is Professor Dr. Director William de Sitter, 1930. He soon changed his mind, and with Einstein, shown here, Einstein on the left, de Sitter on the right, proposed, you know, we're pretty sure the universe contains matter, all those galaxies. We don't know that there's lambda is present, and we don't need it if we abandon this notion of an equilibrium. Let us drop lambda. Let us drop space curvature. This is the elegant theory of the universe, and one that many subscribed to in later years until we were forced away from it. And I turn now to some of the evidence that showed us, first, that the universe did expand from a dense state, reinforcing other evidence, and that to account for the fossil pattern of distributions of galaxies shown in the top and of this thermal radiation shown in the bottom give us strong guides to the presence of this lambda. In the image below, this is a greatly magnified depiction of the temperature variations across the sky. The radiation, these are departures from uniformity at the parts in 100,000. Very tiny fluctuations, real and important, and fossils from the evolution of the universe, but tiny. Measurable, however, with startling precision. So how do we get to this interpretation of the distribution of matter and radiation? Here in the middle is Jerry Yu, my first student. On the left, Bob Dickey, my teacher. And on the right, David Wilkinson at a conference. Here is work Jerry and I did. On the right is an illustration that as the universe expands, some wavelengths are enlarged or favored over others. The phenomenon is familiar to you in many settings. One is a water bottle across which I blow, but we can't do that. Here's another illustration. I have a container, a plate. In it is some water. I shake the plate. The surface is rough. You see chaotic. But yet you also see patterns. You notice that the waves line up with the boundary. It's an effect of a boundary condition. We have a similar effect in the expanding universe. The universe started out very nearly exactly uniform. tiniest of departures from uniformity. These departures grew, but at a time set by the start of the expansion. In the early universe, when the temperature was high, matter was ionized, interacted strongly with radiation, and so matter and radiation acted as a fluid, almost ideal, but slightly viscous. This fluid shook, and it shook until the temperature dropped to about 4,000 degrees Kelvin. This is my musical performance. Now beware, this is beautiful music. You notice a characteristic frequency. It is set by the length of the bottle. The length of time required for the wave to go down and back up sets the period. In a very similar way, the departures from uniformity in the matter radiation fluid in the early universe reverberated at characteristic lengths set by the time at which matter recombined, released the radiation. We have this concept that some waves are favored over others. The amount of the waves that are favored have a length that depends on the expansion history of the universe. So we have a probe of how the universe has been expanding. Here, an example of a wrong step. It's good to notice that science doesn't advance in a regular way. It's chaotic. Here, a paper dated 1980. Two groups have discovered large-scale irregularities in the microwave background. One of the groups was at Princeton. I had to make a theory to explain this. It turned out that the claimed detection was false. The theory is wrong, so I abandoned it. It was an elegant theory, apart from that one problem. And in desperation, I turned to another theory, shown here. You're not supposed to read this, but only to appreciate it exists, that it required two hypotheses. First, that most of the mass of the universe is not in the matter of which you and I are made, baryonic, but rather in a new component that does not interact with anything else except through gravity, dark matter. Not a term I invented, though I can't think of a better one. This theory had another component required. Einstein's lambda, his cosmological constant, is present. Indeed, now, new measurements in the last 10, 20 years, not with this data, but rather more modern mapping of the distribution of galaxies, show that the galaxy distribution does have a pattern in it. Some wavelengths are favored, other wavelengths disfavored. And that this pattern of wavelengths favored and disfavored in the matter distribution, of course, is reflected in the distribution of the radiation, which was in the early days interacting with the matter strongly through radiative drag. And indeed, this has been now measured to exquisite precision. You see the oscillations, you perhaps can't see the theoretical curve, a spectacular fit, really gorgeous. It's worth pausing to notice that the data you saw on that last slide was obtained by the European Space Agency satellite named Planck. Here's an illustration of it. Very high tech. Yet I'm charmed to notice that Bob Dickey's invention, here published in 1946, contains key elements of that radiometer. You see, it was early days. Perhaps you can read at the right-hand side, output meter. When was the last time a big scientist used an output meter with an arm that swung back and forth, a needle? Totally different technology, and yet the basic physics is much the same as in these big horns around the edge. The smaller horns are using another technology not known in Bob Dickey's early work through radiometers, solid-state physics of great precision. But yes, science marches on, using new results and old ones. And now we have, well, I guess I should pause to remark briefly. This curve requires specific values for Einstein's lambda, for the mass density in this hypothetical cold dark matter, for the mass density in ordinary matter. It has adjustable constants. It gives an exquisitely good fit, and so one pays a lot of attention to it. But if we had only this test of our ideas, you might feel a little nervous because bright young people can be wonderfully inventive. If you give them a task, they may solve it, and not necessarily in the right way. They'll present you a fit, and you don't know whether it's the right fit. It's so important, therefore, that we have checks. I illustrate just one. Here is a photograph of a star cluster in our galaxy. The stars have different masses. When stars are of a given age, then the mass determines both the luminosity, which is plotted increasing upward, and the surface temperature, which is plotted increasing to the left. The stars in the lower part are still young in terms of evolution. They're still radiating through energy derived by conversion of hydrogen to helium in the core. The more massive the star, the more rapid the conversion, and at a sufficient age and sufficient mass, the stars will have exhausted the helium in the center, and the relation and their luminosity and temperature will start changing. The shape of this curve marches out the temperature and surface density, surface temperature and luminosity of galaxies in this cluster. And a theoretical line, the parameter along this line is the mass, low mass down to the lower right, high mass up in the upper right. The parameter that is adjusted is the age of this star cluster. It has been known for quite some time now that these old star clusters are around 13,000 million years old. Known rather precisely. And until we had lambda, a serious embarrassment, because they're too old to fit in the universe without lambda. Lambda saves the day because it speeds up the expansion of the universe at late times. And if you think about that a while, you'll see it allows a universe to be old for a given rate of present expansion. Yeah, that's right. This gives us an age that agrees with the theory that fit those other measurements. I could go on at some length about this, but I will simply content myself with saying we have quite a few independent measurements that all agree on this model of a universe whose matter is dominated by hypothetical cold dark matter and which has this curious lambda term. This is our theory of the expanding universe. It's wildly incomplete, you notice. We don't know what the dark matter is. I don't apologize for that because, of course, what can we do? We can only keep looking. Also, you must understand, although the theory is manifestly incomplete, since we can't say what this dark matter is, all of our theories are incomplete. This one is a particularly manifest incompleteness, but it's the general rule. You accept the theory as a good approximation to reality when it fits many measurements, and that's the case here. Just though, to show a little bit of where we stand, I offer an essay written by Thomson Lord Kelvin at about 1900. Thomson had good reason to know that the theory of electromagnetism and the theory of dynamics are solid. His physics is solid. He knew that because he owed his fortune and his peerage to income from patents for transoceanic telegraph lines. He knew perfectly well that his science is good. There were only a few clouds on the horizon. The two clouds, and the essay is celebrated for this region, were the two early hints that we need to have a relativity theory and we need to have a quantum theory. He knew he had the reality, but of course he didn't. There were clouds on the horizon. I point to what is to me the most vivid cloud on our horizon. Somehow that's out of order, isn't it? Oh, no. In fact, this is what I meant. So here's the Abbé Georges Lemaitre again, Einstein on the right, the director of physics at Caltech, Millikan on the left. If you have good eyes, you can see Albert's signature down below. If you have the original, you can see that Millikan signed it too. And I have spent a little bit of time scanning Lemaitre. Did he sign it in black ink on that black habit? Impossible to tell. At this time, Lemaitre was very interested in the idea that Einstein's lambda may be present. He argued with Einstein, politely I'm sure, that he ought to consider lambda. Einstein, on the other hand, felt it was an unnecessary fifth wheel. Inelegant. We don't need it. Let's not have it. But there were hints of problems. Here is the great Austrian physicist Wolfgang Pauli, who in his youth wrote a much admired treatise on relativity theory, and in later years a much admired treatise on quantum physics. This is 1933. In it, he points to the result, the then well established, of zero-point energy in quantum mechanics. To get the right binding energies of atoms, to get the structures of atoms, molecules, you must accept that zero-point energy is a real phenomenon, predicted by quantum mechanics, abundantly tested by experiments. It's real. But what he pointed out is that the electromagnetic field also has zero-point energy in such abundance that the energy density and the zero-point energy of the electromagnetic field would produce an absurdly strong curvature of space-time in Einstein's general relativity. He then wrote what seemed to me simply amazing for a first-rate physicist. It is evident that the zero-point energy cannot exert a gravitational field. But that was just nonsense. You knew it had to. But he couldn't think what else to do. This zero-point energy is absurdly large, if we can understand the theory correctly, and we obviously don't. But it does have the properties of Einstein's lambda. It's just too big by some hundred orders of magnitude. Can you read it? Lemaitre had written to Einstein, repeating again his thoughts that there is merit in considering the cosmological constant. You remember, this is well before we had evidence that the cosmological constant is there. In response to Lemaitre's letter, Einstein writes, "Thank you very much for your kind letter," and so on. "Since I have introduced this term, I had always a bad conscience, but at that time I could see no other possibility." He is repeating what Pauli would have said too when he said, zero-point energy can have no gravitational influence. He couldn't think what else to say, even though it was arrant nonsense. Now, perhaps Einstein has a stronger argument than that. "I cannot help to feel it strongly, and I am unable to believe that such an ugly thing should be realized in nature." There we have it. Einstein, a great physicist, feels that lambda is ugly. Pauli knows that lambda is ugly, perhaps, but my theory, the best theory we have of matter, produces a lambda, but it's absurdly large. Isn't that wonderful? We certainly have something to learn. Is this a cloud on the horizon of these beautiful data? Absolutely. Does it falsify these data? Absolutely not. It tells us, though, that there is a better theory out there waiting to be discovered. It is a gift that I pass on to you, the younger scientists. And I conclude now by simply reminding you that indeed, science is done by people. I've talked about some of these. I could go on for hours about others. People, devoted scientists who have given us so much, from the technology that allows this imaging and allows your cell phones, which I depreciate, to a discovery of the expansion of the universe and a demonstration that it almost certainly did happen. And for the future, you have abundant opportunities to do still more. I'll stop there. Thank you.